Let's start with a simple idea. Imagine you want to describe a car. You could list its properties everywhere you mention it. You could say it has a color, a top speed, and a current number of passengers. This works, but honestly, it can get messy. What if you have many cars? You would have to repeat these descriptions over and over again. Object-oriented programming, or OOP, offers a much cleaner way. It lets us create a blueprint for what a car is. This blueprint is called a class. It defines the properties and actions that all cars will have. It's a way of organizing our thoughts and our code around real-world things. From this single blueprint, this car class, we can create individual, unique cars. Each one is called an object. One object could be a red car, another a blue one. Each object holds its own specific information, like its color being red or its current speed being 60 miles per hour. Yet they all share the same fundamental structure defined by the class. We can also define actions or methods in our blueprint. For example, a car can accelerate, brake, or add a passenger. These actions are part of the blueprint, so every car object we create automatically knows how to perform them. So, at its heart, OOP is about bundling data and the functions that operate on that data together. Think of it like a neatly organized box. Instead of having car properties scattered in one place and car actions in another, the car object holds everything related to it inside itself. This makes our code incredibly intuitive. When we want to make a car do something, we just tell that specific car object to do it. This approach keeps our code tidy, easy to understand, and much simpler to manage, especially as our projects grow in complexity and scope. This concept is a cornerstone of modern programming in languages like Python. It shifts our thinking from a long list of instructions to a world of interacting objects. Each object is responsible for its own state and behavior. This is a powerful mental model. It allows us to build complex systems by thinking about how different components interact, just like how different parts of an engine work together. This organization is not just for neatness. It fundamentally changes how we solve problems, making our solutions more robust and scalable for the future. Now, let's connect this idea to the world of data analytics and machine learning. Imagine you are working with a data set of customer information. Without OOP, you might have separate lists for customer names, ages, and purchase histories. To find the total spending for one customer, you'd need to find their position in one list and use that same position to look up their history in another. This can become very confusing and is prone to errors. It's like having puzzle pieces for a single picture scattered across different boxes, making it hard to see the whole image clearly. With OOP, we can create a customer class. This class acts as a blueprint for a single customer. The blueprint would state that every customer object must have a name, an age, and a list of their purchases. We can also include methods like a function called calculate_total_spending that adds up all the purchases for that specific customer. Now, instead of managing many separate lists, we have a single list of customer objects. Each object is a self-contained package, holding all the relevant information and a built-in tool to analyze it. This is far more organized. This becomes even more powerful in machine learning. Consider building a model to predict something. We can create a model class. This class could have properties like the type of algorithm we are using and its specific settings or hyperparameters. It could also have methods like train, which feeds data to the model, and predict, which uses the trained model to make a new prediction. Each time we want to try a new model or different settings, we just create a new model object. This keeps our experiments clean and separate from one another. This is exactly how many popular data science libraries work under the hood. When you use a library like scikit-learn, you are interacting with objects. For example, you might create a linear regression object or a random forest classifier object. Each of these is an instance of a class that someone wrote. These classes cleverly package all the complex math and logic needed to make the model work. You don't need to know every single detail. You just need to know how to create the object and use its fit and predict methods. OOP makes these powerful tools accessible. The true benefit of using OOP over simple non-OOP code, often called procedural code, is about structure and scalability. In a procedural approach, you have data and functions that are separate. A function might take some data, process it, and return a result. This works well for small, simple tasks. However, as your project grows, you might find yourself writing very similar functions for slightly different types of data. You might also accidentally modify data in a way you didn't intend, because there are no safeguards protecting it. It's like having all your tools lying on a single workbench. Things get cluttered fast. OOP, on the other hand, provides a robust structure that prevents this kind of chaos. By bundling data and methods into objects, we create self-contained units. This principle is called encapsulation. It protects the internal data of an object from being changed accidentally from the outside. You can only interact with the data through the methods the object provides. This makes your code more predictable and easier to debug. If there's a problem with a customer's data, you know the issue must be within the customer class, not some random function elsewhere in your code. Another powerful feature of OOP is inheritance. Imagine we have our customer class, but now we want to define a special type of customer, a VIP customer, who gets a discount. Instead of writing a whole new class from scratch, we can say that the VIP customer class inherits from the customer class. This means it automatically gets all the properties and methods of a regular customer, like name and age. We can then add new things, like a discount underscore rate property, or modify existing methods, like calculate underscore total underscore spending to apply the discount. This saves a massive amount of time and reduces code duplication. Ultimately, this structured approach makes our work reusable and maintainable. When you write a class for a specific task, like cleaning a certain type of dataset, you can easily reuse that class in future projects. If you need to update how the cleaning works, you only need to change it in one place, the class definition. Everyone using that class will automatically get the update. For large data analytics teams, this is essential. It ensures that everyone is using the same logic and that the code base remains consistent and manageable over time, which is something procedural code struggles with. While Python's object-oriented nature is incredibly useful for data analytics and machine learning, its applications extend far beyond these fields. The principles of organizing code around objects are universal. For instance, in web development, popular Python frameworks like Django and Flask are built entirely on OOP concepts. A web page, a user account, a blog post, each of these can be represented as an object. This allows developers to build complex database-driven websites in a logical and organized manner, where each component of the site is a manageable, self-contained object. The world of game development also relies heavily on OOP. Think about a video game. Every character, enemy, weapon, and item in the game world can be an object. A player object would have properties like health and inventory, and methods like move or attack. An enemy object would have similar attributes but might have different behaviors. OOP allows game developers to manage the complex interactions between hundreds or even thousands of these game elements in a way that is both intuitive and efficient, making the game world come to life. Furthermore, OOP is a cornerstone of graphical user interface development. When you see a window on your screen with buttons, sliders, and text boxes, you are looking at a collection of objects. Each button is an object of a button class. It has properties like its label and color, and it has a method that defines what happens when you click it. Libraries like pyqt or tkinter use OOP to let developers build complex applications by combining these pre-built visual objects, much like snapping together building blocks to create a larger structure. Even in scientific computing and simulation, OOP proves invaluable. Scientists can model complex systems by representing real-world entities as objects. A biologist might create an ecosystem object containing animal and plant objects, each with its own rules for interaction. A physicist could simulate planetary motion by creating planet objects that interact through gravitational forces. This object-oriented approach allows for the creation of powerful, realistic simulations that closely mirror the structure of the system being studied, showcasing the true versatility of this programming paradigm.